this is the screencast for section 6.2, example 7, setting up a substitution with a trigonometric identity. So you used a simple identity in the last example. You know, tangent is sine over cosine, or cotangent is cosine over sine. But what about here when we have trig squared? So you might have to use those trig identities from pre-calc. Find the indefinite integrals. In each case, you can use a trigonometric identity to set up a substitution. So you've got to have those trig identities memorized. So part A, the antiderivative of dx over cosine squared of 2x. Now, I don't know the antiderivative of cosine squared of 2x, but it's in the denominator. Thinking, what if I changed cosine squared to 1 minus sine squared? Well, I still don't know the derivative of that, or antiderivative of that, and that would be in the denominator, so that's messy. How about this? Isn't cosine in the denominator secant? So I can push my dx off to the outside, and that would be the antiderivative of secant squared of 2x. I know the antiderivative of secant squared. That's tangent. So now I look at my u as being the inside of this composition function, where the outside of the composition is secant squared of u. So now u is going to be 2x, which means du dx is just 2, and then dx is du over 2. So I can substitute those back in, and I get the antiderivative of secant squared of now 2x we decided to call u, and then dx, the substitution went in du over 2. So I can put my 1/2 outside the antiderivative symbol, the integral, and then take the antiderivative of secant squared, which is tangent of u, and then plus c, and now just plug what u is. So 2x back in, 1/2 tangent of 2x plus c. Now, of course, you could verify that too, and make sure that when you take the derivative of 1/2 tangent of 2x plus c, you get your integrand 1 over cosine squared of 2x, or secant squared of 2x. Part B, the antiderivative of cotangent squared of 3x dx. Let's see. Cotangent. Cotangent is cosine over sine, so I could do cosine squared over sine squared, but I don't know the antiderivative of either one of those. That just seems like messy. I do know a trig identity where cotangent squared is cosecant squared x minus 1. So what if I change this into the antiderivative of cosecant squared of 3x minus 1? Well, now I can split up the antiderivative over that subtraction sign, and I have the antiderivative of cosecant squared of 3x dx minus the antiderivative of 1 dx. Now the antiderivative of cosecant squared is cotangent, so that's good. But the problem is I still have a composition function in that first antiderivative. 3x is a function itself, so I'm going to have to use u substitution on this, and u is going to be 3x. Alright, so then du dx is going to be, du is just going to be 3 over dx. I just solved that one quickly. So here we go. Substitute in the u for 3x, and then for dx I got du over 3. Now here the antiderivative of 1 is x, and then I have my plus c, which I could add later because I still haven't finished taking my antiderivative, but either way. The antiderivative of cosecant squared is in fact negative cotangent, don't forget that. All the cos, derivative of cos are negative, so the antiderivative of cos are also going to be negative. So I've got negative 1/3, the 3 was in the denominator, of now cotangent of u minus x and then plus c, but I've got to substitute back in what u is, and that would be 3x. So there's my final antiderivative. Basically, we came up with a trig identity to break this up into two antiderivatives, one that I could use u substitution with, and the other one that I could just do a straight antiderivative. Part C, another strategy that may seem a little overwhelming. You've got cosine cubed of dx. Well, I don't know cubes very well. Trig really works well with squares, so I think the first thing I'm going to do is separate cosine cubed of x into cosine squared of x times cosine of x dx. Alright, so now, let's see, use substitution yet? No, because if I made u cosine of x, the derivative of cosine is sine, it would not cancel out with cosine, so no. But wait a second. sine and cosine are derivatives of each other, and cosine squared has a trig identity that's got sine in it. Cosine squared is 1 minus sine squared. So now if I have 1 minus sine squared and then times cosine of x, I've got a piece that's related to another piece by a derivative, and I can use u substitution. So I'm going to make u sine of x, because the derivative of sine is cosine, so they will be related. Then the derivative of cosine, or derivative of sine, will be in the denominator. So here, let's try that. So u is sine of x, and then du dx is then cosine of x, so dx equals du over cosine of x. So let's substitute those in. I have 1 minus now u squared times the cosine of x. That stayed there from the original problem. Dx now is being written as du over cosine of x. Oh, messy, messy, messy. All right, so now first of all, the cosines cancel out. That's real nice. But then I can take the antiderivative of 1 minus u squared du, because the antiderivative of 1 is u. The antiderivative of minus u squared is minus 1/3 u cubed, and then plus c. Now I just need to substitute those back in. The u's in for sine of x in for those u's, and then I'm done. So in this one, the strategy was to use a trig identity to get a piece of the identity related to another piece of the function by a derivative, and then use u substitution. Now I'm not saying this is the only way to solve some of these problems. Some of them have definitely more than one way to take the antiderivative of, but these trig substitutions will definitely come in handy for those that there is not more than one way. The now try problem number 47 says use the given trigonometric identity to set up a u substitution and then evaluate the indefinite integral. No problem on the AP exam will tell you to use u substitution. Once you master u substitution and a couple other methods that we're going to learn, the trick will be approaching an integral fresh with no clue how to start it and be able to decide. Are you going to use u substitution? Are you going to use a trig identity? Are you going to use a trig identity and u substitution, or some other method that we haven't learned yet? So that will be the case. Right now, I see an antiderivative of sine cubed of 2x. Now I know I can't just take the antiderivative of that. It's a composition function. So now I need to decide. If I make u sine of 2x, that's u cubed, which I can take the antiderivative of, but then the derivative of sine is cosine, and I don't have any cosines in there, so that's not going to work. But I do have sine cubed, so maybe I'll start out by splitting up that sine cubed into a sine squared 2x times sine 2x dx, like we used as a strategy in the second part or third part of the example. Now this problem is also telling you what trig identity to use, which will not happen on an AP exam or a test either, but that's okay. Baby steps. Alright, so sine squared of 2x can be written as 1 minus cosine squared of 2x, which is nice because then cosine and sine are related by a derivative, and it looks like I can use some u substitution there. So I'm going to make sine squared of 2x 1 minus cosine squared of 2x. So now I'm going to call u cosine of 2x. The derivative of u is negative sine 2x and then times 2 because of the chain rule. So then dx is going to be du over negative 2 sine of 2x. So I'm going to substitute all that stuff in, and I get that the sine of 2x's cancel. I can put the negative 1/2 on the outside of the integral, and then all I'm integrating is 1 minus u squared du. So that's nice. I get u minus 1/3 u cubed. Now remember that negative 1/2 does apply to everything in here, so I had to put parentheses around there or brackets, either one. Alright, next substitute in what u was, and I have my final antiderivative, negative 1/2 cosine of 2x plus 1/6 cosine cubed of 2x plus c. So again, my strategy here was splitting apart the sine cubed into a sine squared times sine, so I could use a trig substitution and get two pieces that are related to each other by a derivative. In this case, it was sine and cosine.